Hey all, this is Derek in this section 11.1, Systems of Linear Equations. We're going to look at a couple of different methods for solving these, substitution and elimination method, or sometimes called addition method. And we'll look at 2 and 3 variable problems. And then I'm going to start with some graphing method. We're not actually going to use graphing as a method for solving because it's pretty limited, but it is good for explaining why there's 3 different outcomes, and lets me introduce the some of the terminology for the section. So basically what we have, if we're solving a system of linear equations in 2 variables, so say x and y, is we have 2 lines. And if we think of the geometry behind 2 lines, one of 3 things can happen if I have 2 lines. I can have 2 separate lines and they cross somewhere, and then that point right there, that point of intersection, is my solution to that system of equations. So we're given these 2 equations, we're asked what would work in both of them, and it's this point that they have in common. So that's an independent, the solution is independent. There's one solution. In this case, it would be 2, 3, it looks like. I could be given these 2 equations, and I graph them, and then they turn out to be parallel lines. So those lines are never, ever going to cross. And so that is called inconsistent. There is no solution because there is no point of intersection. When we go to solve these algebraically, we're going to see that they come out to things like 0 equals 7 or some other sort of nonsensical thing. But what will happen is all the variables are going to drop out of the problem, and then we'll be left with this false statement. So when we see that false statement, that is our heads up that we have an inconsistent system. And then here is dependent. So this was 2 lines, but they disguised one of them, and it was actually the same line twice. And so we graph it, and we graph it again, and it's sitting right on top of itself. So this has infinitely many solutions, not the same as all real numbers, because it's only the points on this line that are the solutions, but there's an infinite number of points on the line. When we go to solve these, they'll be similar to this, except we're going to get some sort of true, yet not very interesting statement like 0 equals 0 or 7 equals 7. And what that means is I can put anything in, and it comes out true. So those are our 3 possible outcomes. And like I said, we could graph any of these things and then look at it and solve that way. Graphing is limited because if it crossed at 2.37, all of a sudden trying to read that off a graph gets really difficult. Likewise, if the point of intersection was out at 1,436, we'd have to draw a really big graph. So you can see that having an algebraic method for getting there is going to be more convenient. Okay, so first we're going to look at solving a system using substitution method. And this is the one that gets used less, and still there's lots and lots of good places that it's the easiest way to go. You'll see when we get to nonlinear systems later in this chapter, sometimes this is by far the best route for solving, and sometimes the other one will be, so it's good to have kind of more than one tool in the toolbox. So to solve using substitution, the first thing we do is isolate one of the variables. And so in this system of equations right here, we're already given this with x equals, so one of the variables is already isolated. That would make me want to use substitution as the method of solving, just because it's already kind of set up for it. 2 is substitute the expression for this variable into the second equation and solve for the remaining variable. So this is x equals negative 5y minus 3, and so we're going to take that and plug it right there for that x into the other equation. So that's going to look like negative 7 and then negative 5y minus 3 minus 4y equals negative 41. And now we just solve for y. So 35y plus 21 minus 4y equals negative 41. 35 minus 4 would be 31y. Let's subtract the 21 over. And that gets us negative 62. Cool, so then we divide this. And it looks like y equals negative 2. So that's the half of our ordered pair, but we have to go back and we have y, so we have to go back and get the x coordinate. And we'll just plug that right into this equation right here because it's already solved for x, so that is super convenient. And that will be the case when we're doing a substitution. So this would be 10 minus 3, so it looks like x is 7. So our point of intersection, or our solution to the system, would be 7, negative 2. So for this next one, it is not isolated for a variable yet. I could divide out that negative 8 and get y by itself, but then it would be terrible and have fractions on this side, so that is not super appealing. I'm looking at that x right there, thinking that would be pretty easy to get by itself. So I'm going to rewrite this as x equals 9 minus 4y. And now I can take this and drop it in for that x. So that's going to give me negative 8y equals negative 18 plus 2, 9 minus 4y. And so basically what I did there is I just kind of tried to pick the path of least resistance, and to me that was the x. Now I just solve this same as the last one. So negative 8y equals negative 18, 2 times 9 plus 18, and then minus 8y. So then let's say I brought this 8y over, just to show what happens. And minus plus, so that would be 0, equals negative 18 plus 18, which is 0. And that's what I meant by we'll end up with something that looks like 0 equals 0. I could have also brought this over and said 18 equals 18. Or just over here, I could have brought this over and said, hey, look, both sides are the same, which means they're the same equation. So whenever you can kind of see that coming, that means you have a dependent system. Okay, so the next tip we have solving systems of equation by elimination, also called the addition method, just depending on which book you're looking in. And then later it gets called the Gauss-Jordan elimination method when we use matrices with it. And so for this, we're going to, let me kind of go through the steps. We're going to write both equations with the x and y variables on the left side of the equal sign and the constraints on the right, which basically just means we want it to kind of look like that. And what we want is for either the x or the y term to have opposite coefficients. And by opposite coefficients, I mean the same number with opposite signs. So like if one of the equations has 5x, I'd want the other one to have negative 5x. And the reason is so when we add them, they would cancel out. So if either the x or the y term have opposite coefficients, yay, just add them together and eliminate the variable. If not, boo, then we have to do some work. We're going to multiply by, we're going to find an LCD and then build both of those terms up to that where we have opposite coefficients. And then we'll do the same thing, eliminate the variable. Once we've done that, then we're down to one variable and we can just solve it and then do the back solve like we did with the last problem. This ends up being the method we use probably the most going forward, and it's definitely the one that we use for higher order problems. So up next will be 3 variables with 3 unknowns, and then this is the method we'll use there. So for these examples, I want to get same number, opposite signs for coefficients. I can either do x or y, it doesn't matter which one. Let's see, what did I do in the notes? I did y, which is what I figured I would do. So here I could have brought both of these up to 12, and I would have had to multiply both equations. Here I can make this one a 10 by just doing a negative 2 to that first equation. So I'll go negative 2 times equation 1. Let me show you what I get. Negative x, or 8x, and then minus 2 times minus 5 makes a plus 10y, which is what we want, equals 2. And then let me write this one underneath it so you can see why I'm doing what I'm doing. Because then when I add these together, the plus 10 minus 10 is going to drop out. So that's why we want these to be opposites, is because we're going to eliminate, hence the name elimination method, by addition. Hence the other name, addition method. So negative 5x, those are gone, equals 20. Bring that over, and x equals negative 4. So we want same number, opposite signs. And then once we have that, we can just go back to either of those original equations. I'll go with the first one arbitrarily. So 4 times negative 4 minus 5y equals negative 1. And then that allows me to back solve for that second variable. So negative 16 minus 5y equals negative 1. Adding that over, negative 5y equals 15. And y equals negative 3. So the solution set here is negative 4, negative 3. One more example using elimination method with 2 variables. So 2 and 3 are smaller numbers, so that would draw my eye. You'll see this actually ends up being, it doesn't matter, but just sort of looking at it initially, I would kind of look at that 2 and the 3. So I'm going to multiply this first equation by a negative 3, because I need one of those signs to get flipped around. So I'm going negative 3 times equation 1. So that's going to give me a positive 6x. Negative 3 times 6 will give me a negative 18y. And negative 3 times negative 16 is positive 48. and then I'm going to multiply this one by 2 so that I get a negative 6x. So I'm just finding the LCD there. So then this is negative 6x, 2 times 9 is 18. You can kind of see what's happening there. And times 28 would be 56 negative. And then this side, 0, everything cancels. But this side is non-zero this time. This is negative 8 as it happens. And so this is an example of an inconsistent system. Okay, so up next is 3 equations, 3 unknowns. And these are going to take the form ax plus by. And now we get plus cz, so we're going to get a z term, and that's going to be basically, if we're graphing, we're going to have a z-axis along with x and y. So this is representing 3D space, and there's 3 possible outcomes again for these systems. And they're the same thing. We can either get a solution, we can get a dependent system that has infinite solutions, or we can get an inconsistent system that doesn't have solutions. And this time, if we were to graph these, which is actually kind of challenging, what we would see is they're, like I said, 3-dimensional planes in space. So one solution just means like all the planes are intersecting at a single point. Like if you think of the floor and 2 walls coming together in the corner of a room, that corner would be a point of intersection, and that would be your solution set for those 3 planes. A dependent solution would be something like this, where all 3 planes are intersecting, but they're intersecting in a line. And then that line represents an infinite number of ordered triplets, or what these are called when we have an x and y and a z. And then for inconsistent, there's lots of different geometry that could do that. So all 3 planes intersect, but nowhere do they all intersect at the same spot. Same 2 parallel, 1 passing through, all 3 parallel. So lots of possibilities for it didn't work, and that would be an inconsistent one. Okay, so this is basically elimination method again. And so let me kind of go through what we can do and what our basic goal is, what our basic plan of attack is. We didn't talk about interchanging the order of any 2 equations in the 2 variable ones because it really didn't matter. It doesn't matter so much when we're solving them this way, but if we're going to use matrix notation, the fact that we can rewrite equation 1 and equation 2 and just flip them and make 2, 1 and 1, 2 ends up being a handy thing. We can still multiply both sides of an equation by a non-constant or a non-zero constant, so that's what we were doing in the last one so that we could get the coefficients to match, and we can add non-zero multiples of one equation to another. So it's that same elimination stuff that we just saw with 2 variables. So our basic plan of attack for these is, and let me grab one that will look like what we're going to be working on. So we pick any pair of equations and solve for one of the variables. So if I picked this, I could pick x, y, or z. Let's say I eliminated the z's out of equations 1 and 2. Then I would pick another pair of equations and solve for the same variable. By solve, I mean eliminate. I should probably change that to eliminate. And so if I picked 1 and 2 the first time, then I could pick 1 and 3 or 2 and 3, but I have to eliminate z again. What that will do is now give me 2 equations and 2 unknowns, which is what we just solved. And then we just solve it the way we did. We go and get x, we go and we get y, and then we just have 1 extra back solve. And for that, we go back and get the z. And we could do that in any order. But the idea is to eliminate one of the variables twice, get it down to 2 equations, 2 unknown, solve to get your first variable, back solve for your second variable, back solve for your third variable. So let me show you what that will look like with an example. So this one is 3 equations, and it is 3 unknowns. We do have z's along with our x's and y's. This one is like the too easy it's hard equation. The next example is kind of more the meat and potatoes of this. This one is just kind of it's got this little catch to it, so let me show you. Right now, I could put the first 2 equations together and eliminate x. I could put 2 and 3 and eliminate z. I could put 1 and 3, eliminate y. There's a lot of different things I could do. And what will happen when I do that, let me just arbitrarily pick 2 and 3, since those z's are just kind of sitting there. So I'm going to say equation 2 is this, and equation 3 is this. And then I'll add these together. Be careful, x's and y's are not the same thing, so all I could do is write that as x plus y plus z minus z cancels equals 7. I'm going to name this one equation 4, just to give it a way to distinguish it from 1, 2, and 3 over here. So what you'll see on the next example is the next thing I would do then is put two more equations together and eliminate. When we have only two variables in any given equation, you don't want to do that. In this case, I've used, so there was 1, 2, and 3. I've used 2 and 3. All you gotta do is match up 1 and the one I just made, and the variables are gonna be the same. If you try to put 1 and 2 together, you'll eliminate x's in that case. You'd have y's and z's. It wouldn't match. You'd be stuck. If you tried to put 1 and 3 together, you could eliminate y's, so you'd have x and z. You'd still be stuck. So the only thing to do is after you eliminate two of them, use the one you haven't had, the one you haven't used yet, and then that's going to eliminate something with your new equation. So I'm just going to take equation 1 and drop it right there because those y's are already set up for me. And then that gets me 2x, y's cancel, equals 4, and so then x equals 2. So I got my first of my 3 solutions, and this time we're going to get ordered triplets. So those look like x, y, z. And to get my next couple answers, I'm just going to back solve. So I'll go ahead and come back up here and go. So it looks like 2 minus y equals negative 3. Minus y will equal minus 5. So then y equals 5. And then how about there? We'll go x is 2 plus z equals 0. So z equals negative 2. So my solution set will be 2, 5, and negative 2. So that's how you type it on the computer. Okay, so this one does a little bit more, this is a bit more classic with the x, y, and z present in every equation. So the goal with these is we're going to take two equations, put them together, eliminate a variable, and then we're going to take two different equations, put those together, and then eliminate the same variable. So like for this example, I'm going to eliminate x. And the reason for that is, one, it's not terribly hard. Z might have actually been a little tiny bit easier. I'm going to do the x's because it will go nice with the matrices that we'll do in the next section. But when I eliminate x in this first round, I have to then also eliminate x in the second round. So that's kind of the deal. Because once I get rid of x the first time, I'll have an equation in y and z. The goal is to make another one of those in y and z, and then you put those two together and get an answer. And once you got that, then you can just back solve. So I'm going to do negative 2 times equation 1, and then I'm going to add to that equation 2 right here. So that's going to give me a negative 2x and a positive 2x, and that's going to make those drop out. So that will be negative 2x plus 6y minus 2z equals 2 times 3, 6. And I just have to copy this one over. Okay, and then those cancel, and this is going to give me 8y minus 4z equals 20. And I'm going to call that one equation 4. If you went ahead and put 1 and 3 together right now, x and z actually drop out. I originally did that in the notes and went, I didn't want it to do that. If it did do that, that's great. That's actually really nice. You could take, because the x and the z would have dropped out, when you did this by negative 2, you would have known y. You could plug it right here, get z, go back and get x, and you'd be done. I'm going to do this specifically to get an equation 5 so that I can show you that step though. So I'm going to, what I probably would have done if it didn't do that was just go negative 2 times this and do it to the next one. Instead, I'm going to go negative 1 times equation 2. And then I'm going to add to that equation 3, because again, I don't want the variables to drop out because I want to be able to show you all the steps. So this is going to be negative 2x minus 2y, and then plus 2z makes negative 14. And then here, and then we'll add these together, and the x's drop out. That was the plan. And I get y plus 4z equals negative 11. So I'm going to call that one equation 5. So that's pretty typical of how these will solve, is you put two of them together, you eliminate a variable, you put two different equations together, and then eliminate the same variable. And then you're at this kind of equation 4 and 5, as I call them, which is just two equations with two unknowns. And then that's what we were doing earlier in the section where we just solve and eliminate one of these. The z's are already set up to work out great, so I'm just going to do equation 4 here and add to that equation 5. Okay, so then here's our equation 4 and 5, and then 8y plus y makes 9y, minus 4z plus 4z, those just cancel, and then 20 minus 11 makes 9. And then dividing over, we get y equals 1. Once we know that, that's cool. Now I can come back here, so I got our first solution. I can go back to either equation 4 or 5. 5 looks a little easier, so I'm going to go right here with it. So I'm just going to say 1 plus 4z makes negative 11. 4z makes negative 12, and z makes negative 3. So there's my second solution. And then I'll come back to whichever one of these looks the easiest, which I guess is probably equation 1. And then I'll just pop these in, and I'll grab my last variable, which will be that x. So this will be x minus 3 times y is 1 plus or minus 3. So we'll call that minus 3, negative 3. So x, that will be minus 6 equals minus 3, add it over, and x equals 3. So our solution set is 3, 1, and negative 3. So looking at this problem, I think I will eliminate the x's just because that seems like the easiest way. So I'm going to go equation 1, and then I'm going to go negative 2 times equation 2, and that'll give me a plus 2 and a minus 2 right there, and I'll cut away and then write all that out. Okay, so here's equation 1, and then here's negative 2 times equation 2, and then adding those cancel. Y plus 4y gave me 5y, down 3 up 2 gets me minus z, and then 1 minus 6 gave me minus 5. So I'm going to call that one equation 4. And then I'm going to go, I think, the negative of equation 2, and then I'll add to that equation 3, and that's going to eliminate x again. Okay, so then putting those two together, the x's drop out as planned. This will be equation 5. And here I'm going to get 10y minus 2z equals negative 10. And so I've made my 4 and my 5, and then this is a spot where I would put those two together and try to eliminate a variable. But you can see if I multiply equation 4 by, say, negative 2, I'm just going to get the opposite of this one. So I'd get negative 2y plus 2z, and then negative 2 times that would be 10. And then 10y minus 2z equals negative 10. So that's our 5. And then everything cancels. So we're at that 0 equals 0. And so that's just an example of dependent with a 3-variable problem. Sometimes on a question, you're able to spot where 2 rows are multiples of one another. So here, if you look at equations 1 and 2, at least the left-hand side of the equal sign, it's just, they're the same thing, but this is multiplied by a negative 2. So just to show the canceling, I'll go ahead and do 2 times equation 1, and then I'm going to add to that equation 2. So 2x plus 8y plus 8z equals negative 8, and copying this one over. And so hopefully you can see what I mean by multiples. So if you see that, you know it's either going to be inconsistent or dependent, kind of depending on what the right-hand side does. And so in this case, the left-hand side all drops out, and over here we have 3, so it's a false statement. So that's the kind that's inconsistent. And often you can't spot them like that, but it's always worth just kind of glancing through and making sure it's not something as easy as that.